Hello to anyone who's watching this video. This is just a short explanation of the work that I will be presenting at TQC this year, and this work is entitled Poly-based Computation with Higher Dimensional Systems. So just a brief overview of this video. I will start with some background concepts that you will need for understanding this work. Then I will move on to explaining poly-based computation with higher dimensional qubits. So in particular, I will focus in odd prime dimensional qubits. I will then explain how we can carry out a poly-based computation in practice. And finally, I will discuss the cost of hybrid computation with qubits of different dimensions. So poly-based computation is a measurement-based model of quantum computation, and this model works by having as input a product state that is the tensor product of T magic states, followed by at most T measurements or T poly measurements that need to be compatible and need to be chosen adaptively. So this is why you see here this efficient classical side processing that is necessary to happen during the computation, which comes from the need to decide what the second poly measurement is going to be based on the outcome of the first, what the third poly measurement is going to be based on the outcome of the other two, and so on. So this is how a poly-based computation looks, and in 2016, Bravi, Smith, and Smalling showed that any universally general quantum circuit C with n input qubits, T gates, and a certain number of measurements in the computational basis can be simulated by a poly-based computation with T qubits in the magic state T, followed by a sequence of at most T-compatible and adaptively chosen poly measurements. So this result is basically a statement on the universality of poly-based computation, because if you can simulate any universally general quantum circuit with a poly-based computation, then necessarily this model needs to be universal. And another alternative way of looking at this result is actually looking at it as a sort of compilation statement. And this was done in a work from last year, where you can see that for some instances of quantum circuits, you can use poly-based computation as a sort of compilation tool that you use to reduce the number or the amount of quantum resources that you need to perform a certain computation. Now to the present work. So this blue rectangle that you see now on the screen is just a snippet of the poster that I will be presenting, and is basically a generalization of the theorem by Bravi, Smith, and Smalling, but now for p-dimensional qubits, where p is an odd prime number. So this is just stating that any universal Clifford plus TP quantum circuit can be simulated by a poly-based computation on T qubits, where T is just the number of magical gates in the original quantum circuit. And at the bottom below the blue rectangle, you just see the magic gate for qubits. Could be, for instance, the T gate. For Q-trits, could be this gate over here, and for Q-quints, this gate over here. And here I just want to point out that this notation is slightly different from the one used on the preprint. So if you check the preprint, a slightly different notation is used, but for the purposes of the poster and for the purposes of this video, I thought that this notation could be easier. Now let's move on to part 2, which is how can we actually implement such a poly-based computation in practice. And perhaps the better way to figure out how to do this in practice is just to bring things back to the circuit model, because this is the model that is better known in the community. And so suppose that you have a 3-qubit poly measurement that you want to perform. And this poly measurement actually is encompassing all the 3 possible non-trivial cases that you can have: x to the power of a, z to the power of b, and x to the power of c multiplied by z to the power of d. And if you want to do such a measurement, then what you do is just to implement this quantum circuit that you see here on the right, where we've brought in an auxiliary qubit on state 0. We transform it using the Fourier gate, which is basically a generalization of the Hadamard gate. Then we apply a cascade of some gates, which are basically the generalization of the C0 gate. And then we apply the adjoint of the Fourier gate and measure the auxiliary qubit. And when we do this, the state that we have here at the end is the same state that we would have gotten if we had performed this measurement and obtained the outcome sigma. So if we use this kind of strategy, it is easy to see that if you have a Pauli-based computation on T qubits, you can transform it into a quantum circuit that has T plus 1 qubits. The plus 1 comes from the auxiliary qubit that we need. And then we have a depth that is quadratic in T. But we can actually have a trade-off here between the depth and width of the circuits, and in particular we can trade time for space, and that is done by bringing in T auxiliary qubits instead of just one, and we bring them in and initialize them in a GHZ state, generalized GHZ state, as you see here. And the advantage of doing this is that now this cascade of some gates can be performed in parallel. And so what you see is that now a certain Pauli-based computation can be translated into a quantum circuit that requires 2T qubits, but now requires only linear depth. And so we have these two methods that we can play with and decide which one is better for the case that we have at hand. And finally, to conclude, we have this hybrid computation setup. And let me explain exactly what is meant by hybrid computation here. So suppose that you have a certain quantum hardware that has a fixed number of qubits, and you have a certain algorithm or a certain Pauli-based computation that you want to run that requires a certain number of qubits, but the number of qubits that is needed is greater than the number of qubits that we actually have available in the hardware, and the difference is k. Okay, let's call the difference k. So the idea is there a way to still run this Pauli-based computation in this quantum processing unit that we have? And the answer is yes, there is a way to do this, but of course we are sort of simulating k of the qubits virtually in a classical machine. And of course, this is going to lead to an exponential overhead. And in particular, this is the cost, the extra cost that we have is a sampling complexity that is driven by the square of the robustness of magic. And the fact that this is related to the square of the robustness of magic means that we can find some lower and upper bounds for this sampling complexity for qubits, qtrits, and qquints. And here I just want to point out that as we change the dimension of the qubits from 2 to 3 to 5, we also change the base of the exponential. So notice here 2, 3, and 5. And the same for the upper bounds. And the reason to do this is that when we increase the dimension of the qubits, immediately we're increasing the size of the Hilbert space. So for a classical machine, immediately this is going to become harder to simulate. So when we change the base, there will be an increased hardness of simulation associated precisely with the fact that we have increased the dimension of the qubits. This is fairly intuitive. And so we are tracking that increased hardness by changing the base of the exponential. But if that's the only thing that's causing an increased hardness, so we should have an increase of the base, and if the exponent is the same across the board, this means that, of course, we have an increased hardness, but this comes only from increasing p. But what we see is actually slightly different. We see that we change the base of these exponentials, but actually the exponents also seem to be growing. So let me bring in a visual aid to help with the explanation. And here you see precisely the sampling complexity and how it grows for qubits, q-trees, and q-quints. And obviously, it grows much quicker for q-quints because immediately the base has changed. So this is going to grow much faster. But like I said, let's just zoom in on what's happening in the exponents. And as I explained before, like if the exponents were the same, then we would say, of course, there is an increased hardness of hybrid of simulating these k qubits classically, but this hardness comes only from the increase of p. But what we see is actually the exponents themselves also seem to increase as we increase p. So there seems to be an additional effect of hardness associated with this hybrid simulation as we increase the dimension of the qubits, and this is quite interesting. And the way you can see this here is, for instance, that you have no overlap between the gray area and the green area associated with qubits and q-quints respectively. So these do not overlap. So clearly the exponent for q-quints is going to be larger than the exponent for qubits. So there's some kind of effect happening here from the increase of dimension, which is an interesting observation. And with this, I just want to finish up with some concluding remarks. I want to note that this work generalizes Pauli-based computation for odd prime dimensional qubits, but the same has not been done for composite dimensions yet. Then I want to also point out that the upper and lower bounds that were presented were obtained using the specific scheme, this specific Monte Carlo type of algorithm that was used to perform this hybrid computation. So maybe these bounds can be improved with other kinds of strategies. And in fact, that would be an interesting future line of research, trying to figure out what is the optimal approach to this task of extending the quantum memory by a certain number k of virtual qubits. And would this seeming increase of hardness as you increase p, would this remain, with this observation remain if we found that this optimal approach? This could be an interesting line of research. And finally, just thank you for watching this video until the end. If you are interested in this work, this is a snippet of the poster that I will be presenting. Please approach me at TQC and we can discuss this a little bit further, or just email me if you are not able to attend, and check the preprint for any details. Again, thank you, and hopefully see you at the conference.